Solving a quadratic equation by using a square root. Now, we've solved equations for solutions before. The following equations are similar, but the x squared changes the way we perform the final steps in solving. It's a clue about the number of solutions that we will have. Now, when we do have that x squared, or a quadratic, we need to identify when it is factorable. On the left, we've got a standard quadratic, x squared minus x minus 6 equals 0. It's a standard quadratic trinomial. We can factor and solve that. We've done that before. Grab my pen tool here. So, since it's a standard quadratic, I know that I will have two sets of parentheses and set it equal to 0. Okay, factors of 6 and negative 6 more specifically would be either 1 and 6 or 2 and 3. Their difference needs to be 1, so I know I need to use 2 and 3. The larger value needs to be negative because my sum is negative. From there, I would set both terms equal to 0 and solve to get x equals 3 and x equals negative 2. And again, we can do that because that was factorable. On the right side, x squared minus 6 equals 0. Okay, this is not factorable. Okay, there is no x term, and it is not a difference of squares. Okay, 6 is not a perfect square. It is a difference, but it is not a difference of squares. There's no x term. It's not a trinomial, so I cannot factor this. It's going to change how I'm going to solve. I need to solve this one by taking the square root. Well, this is something you've done before in geometry by using the Pythagorean theorem. Okay, if I were to solve for x here, I know that the Pythagorean theorem says a squared plus b squared equals c squared, where a and b are the legs and c is the hypotenuse. So if I were to solve for x, I would say that x squared plus 6 squared, since those are the two legs, have to equal my hypotenuse squared. Well, when I simplify, x squared plus 36 equals 100. Isolate x, subtract 36. X squared is going to equal 64, and my final step is to take the square root. And remember, when I take a square root, okay, I get two solutions. Okay, 8 times 8 is 64, but negative 8 times negative 8 is also 64. So I need to include the positive and negative parts. Okay, when we solve by square root, we have to include the plus and the minus. Example 1, solve by taking the square root. Isolate x by using the inverse order of operations. Remember our order of operations. And I'm going to undo these. So I'm going to do the inverse order. Get rid of any addition and subtraction. So I'm going to subtract 5. That gives me 3x squared equals 36. Get x by itself. X squared equals 12. To solve for x, I take the square root. And I'm taking square root because squared and square root are inverse operations, just like plus and minus, multiply and divide. Okay, they undo each other. Okay, so I get x equals plus or minus 12, which can be broken down into its perfect square factor, 4 and 3. Okay, I chose 4 because it's a perfect square. It's the biggest perfect square factor of 12. So x is going to equal plus or minus, the square root of 4 is 2, and then I tack on that root 3. That's my answer. My two solutions, two possibilities. Okay, we have to include both plus and minus because a negative times itself yields that positive solution. Example 2. Again, inverse order operations. I add 15. I get 2x squared equals negative 50. Divide by 2. So x squared equals negative 25. And this might be a red flag because when I take a square root, I now have a square root of a negative. Well, good thing we just talked about imaginary and complex numbers. Okay, I want to get that negative sign out, so I'm going to factor out the square root of negative 1, leaving behind a perfect square, the square root of 25. Okay, thinking back, the square root of negative 1 is I. Okay, some of you are probably yelling at me because I forgot my plus or minus, plus or minus, plus or minus. Okay, and the square root of 25 is 5, so I'm multiplying that by 5. I get plus or minus 5i. And those are my two possible solutions. Example 3. Okay, I've got two separate x squared terms. I want to get all of those together. I've been working with them on the left side, so we might as well move them all over there. Okay, when I add x squared, that's adding a 1x squared. I got my x squareds to the left side. I might as well move my constants to the right side right away. So when I simplify, 3 and 1 give me 4x squared equals 9 plus 5 is 14. Divide by 4. I get x squared equals 14 over 4. 14 over 4. Okay. Some of us may be thinking, oh, I can simplify that, but before I do that, notice 4 is a perfect square. So when I take the square root of both sides, okay, I get plus or minus root 14 over root 4. Okay, and if I were to have simplified that before, I would need to rationalize this denominator, but since the square root of 4 is a perfect square, that denominator will rationalize all on its own. So I get plus or minus root 14 over 2. Okay, only factors of 14 are 1 in itself, 2 and 7. Okay, 2 and 7 are prime. Okay, so I cannot simplify the square root of 14 any further. That one is done. Got two more examples. Okay, this one's a little different. Okay, I've still got a squared. Okay, some of us are thinking, well, a binomial squared, okay, I can rewrite as two sets of parentheses. However, I can bypass that step. Okay, I can take the square root of both sides immediately. Okay, I'm square rooting that entire thing. Well, when I do that, that squared is gone. Okay, so I have x plus 9 equals the square root of negative 4. Okay, there's nothing else outside of those parentheses. So those essentially just drop away. Oops, erased too much there. Okay. Well, on the right side, let's get rid of that square root of a negative first. So I can factor out that negative 1, which is awesome because 4 is a perfect square. Okay, the square root of 4 is 2. The square root of negative 1 is I. To get x by itself, subtract 9. Okay, thinking back to a complex number, when I simplify them, I want my real part first, followed by my imaginary. Okay, one thing I forgot when I took that plus or minus, that 2i needs to be plus or minus. Okay, so those are my two solutions. X equals -9 plus or minus 2i. Last example here. This one gets a little bit long, so if you're following along on my foldable sheets, make sure you write small. Okay, based on our inverse order of operations. Okay, the last one is subtract in PEMDAS, so I get rid of the subtraction first by adding 1. I am left with 3x plus 9 squared equals 40. The next inverse order operation would be to divide out that 3. Again, if I'm following PEMDAS backwards, multiplication would come next. So I get rid of that by division. I am left with x plus 9 squared equals 40 over 3. And I'm going to leave that as that fraction. I can't simplify that. I can't factor anything out. I can't reduce it, so I'm going to leave it for right now. Okay. Now, when I take the square root, okay, I am left with x plus 9 equals plus or minus, and I'm going to break up that radical. So I'm going to write this as root 40 over root 3. And I'm going to do that because 40 has a perfect square factor. Okay, perfect square factor there would be 4. So x plus 9 is going to equal plus or minus. I'm going to break up root 40 into root 4 times root 10. And that's all over root 3. Okay, I'm going to do another step all at the same time. I have root 3 in the denominator, so I'm going to rationalize this right away. I'm going to multiply top and bottom by root 3. I'm going to bring this up here. So I have x plus 9 on the left equals plus or minus. The square root of 4 is 2. Root 10 root 3 is root 30. And there are no perfect square factors of root 30. All over, and we rationalized and got 3. The square root of 3 squared is 3, or root 3 times root 3 is root 9, and root 9 is 3. The last thing I have to do is get x by itself by subtracting 9 from both sides. Okay. I'm going to write the whole number first, plus or minus 2 root 30 over 3. And that's my solution. I know it looks a little odd, okay, but I avoid decimals, and that's an exact answer. Okay, that's my exact answer. Thanks for watching. Thanks for taking notes. Catch you on the flip side.